Imagine strolling along a quiet beach at dusk, when a smooth, unfamiliar stone skids past your feet, flung from somewhere beyond the horizon. That surprise captures the feeling astronomers had on 19 October 2017, when the Pan-STARRS telescope in Hawaii flagged an object racing through the inner solar system, faster than any known comet. Its path wasn't a closed ellipse like our resident planets, it was a one-off hyperbola, proof that this traveler had come from another star and would never return. In keeping with Hawaiian tradition, it was named Oumuamua, a messenger sent first to reach out. Newsrooms pounced because this was, quite literally, the first time humanity had caught an interstellar visitor in the act. Suddenly, the abstract notion that other suns eject rocky debris became tangible. If a shard of an alien world could casually drift across our sky, what else might be out there, Oumuamua, and how could we prepare for the next cosmic knock at our door? In one swoop, Oumuamua turned planetary science into breaking news for the world. It was 11:59 p.m. local time on October 19, 2017, when University of Hawaii postdoc Robert Warwick opened a batch of fresh images from the Pan-STARRS 1 survey telescope perched on Halakela. One faint streak leapt across the field like a dash of chalk. At first glance, it looked like just another near-Earth asteroid, but when Warwick measured its track, he saw trouble. The object was barreling toward the constellation Lyra at nearly 87 kilometers per second, far faster than typical inner solar system wanderers. He plugged the coordinates into the Minor Planet Center's automatic checker. The return email was almost empty. No matches in the catalog. Curious, Varric compared data from the following night and recalculated the orbit. The eccentricity popped out at 1.20, a hyperbola, steep enough to escape the sun forever. Within 24 hours, Karen Meach and colleagues fired off urgent alerts to observatories worldwide, and 20 global telescopes, from Arizona to Chile to the Canary Islands, rapidly pivoted to the fading speck. Each new data point confirmed the same impossible geometry. This thing had never been bound to our star, because it was already past its September perihelion. Astronomers had barely a few weeks before the magnitude plunged beyond reach. The International Astronomical Union fast-tracked a name: 1I/Oumuamua, first messenger. Discovery Day thus became a sprint, a scramble, and the start of a brand new field, interstellar object astronomy. In orbital diagrams, most comets trace lazy ellipses pinned to the sun like marbles in a bowl. Oumuamua instead sliced across the dish on a hyperbolic curve, an open-ended swoop whose arms never reconnect. Put numbers on that curve and its foreign pedigree is obvious. An orbital eccentricity of 1.20, inbound speed of 26 kilometers per second beyond Neptune, and a heliocentric sprint that peaked near 87 kilometers per second at perihelion. That closest approach happened on September 9, 2017, when the visitor skimmed just 0.25 astronomical units, 1/4 Earth-Sun distance, above the solar furnace. Even then, telescopes missed it. The rock was simply too small and too fast to linger in the glare. Freed from solar grip, it crossed Earth's orbital plane on the 14th of October 2017, passing 0.16 astronomical units ahead of our planet, about 60 lunar distances. By discovery night 5 days later, it was already outbound past 1 astronomical unit, its brightness fading half a magnitude every 2 days. No spacecraft built by humans could hope to match that exit speed. Oumuamua was literally outrunning the technology of 2017. Project the track backward, and it seems to have entered the solar system from the Lyra-Hercules gap, nearly perpendicular to the ecliptic. Forward in time, the same equations show it will glide toward Pegasus, slipping into interstellar dusk and cruising at 26 kilometers per second relative to the galaxy, fast enough to cross the span between sun-like stars in a few tens of millions of years. Worldwide observatories were laid across time zones to keep the fading messenger in view. Its dash was brief, only 11 weeks inside Mars's orbit, but it rewrote textbooks on what can and will wander through our celestial backyard. Oumuamua revealed its shape only by the starlight it blocked and reflected, leaving astronomers to decode a flickering silhouette. Over 11 observing nights, its brightness swung by 2.5 magnitudes, a tenfold change. The simplest reading is that a long axis, sometimes aimed toward Earth and sometimes turned edge-on, like a tossed baton. That amplitude implies an axis ratio of at least 6:1. Tie the light curve to thermal limits from Spitzer, and two cartoons emerge: a 225 meter by 35 meter cigar, or a 100 meter wide pancake, no thicker than a city block. Either way, it is dramatically elongated compared with most asteroids. The spin adds another twist. Instead of rotating smoothly, Oumuamua is tumbling on two axes, a non-principal axis state. Photometry shows a dominant period near 8.1 hours, yet the peaks drift, implying a slower wobble that takes days to repeat. Tumbling is easy to start. One glancing impact or tidal shove in its birth system would do, but nearly impossible to damp without internal friction, so the chaos could have persisted for hundreds of millions of years. Surface hints are scarce. Its reddish tint matches carbon-rich organics baked by cosmic rays, much like Kuiper Belt relics. Thermal models show the searing perihelion pass would have vaporized hidden ices, perhaps peeling layers off a fluffy structure and even flattening it. Taken together, the variations suggest a body no larger than 200 meters across its longest dimension, cloaked in a veneer of space-weathered dust. Whatever the exact silhouette, Oumuamua's wild light curve shattered the tidy textbook notion that small bodies are bowling ball solids. Some are cosmic splinters, or crepes, flung from alien star systems to puzzle us in passing. When astronomers stitched together post-discovery positions, the best-fit orbit wouldn't sit still. The object drifted a hair outside the track dictated by gravity alone. An outward shove of roughly 5/10,000ths of a meter per second squared. Tiny to us, but huge for a 100-meter rock. The statistical significance cleared 30 sigma. The effect was real. In a normal comet, that extra thrust would come from water vapor roaring off sun-warmed vents, dragging dust and sculpting a luminous tail. Yet the Very Large Telescope, Hubble, and the Canada-France-Hawaii Telescope stacked deep images and saw nothing. No fuzzy halo, no streamer, no spectral hint of gas. The dust production rate had to be below a single gram per second, 3 orders of magnitude quieter than comets of similar size. The contradiction lit a theoretical bonfire. One camp suggested Oumuamua was a shard of super volatile ice, pure hydrogen, nitrogen, or carbon monoxide snow that sublimates invisibly and leaves no dust. Another proposed it was a porous, centimeter-scale dust bunny as light as aerogel. Such a fluff ball could feel enough solar radiation pressure to mimic outgassing. The most sensational idea came from Harvard's Avi Loeb and colleagues. Perhaps the nudge was sunlight on an artificial light sail only millimeters thick, a relic of extraterrestrial engineering. Follow-up studies poured over the energetics, showing each hypothesis strained but did not break known physics. What everyone agrees on is that the unexplained acceleration transformed Oumuamua from a statistical milestone into a cosmic riddle, one whose answer is still racing away, 12 million kilometers more distant every day. With no coma to sample and no probe to sniff its surface, Oumuamua leaves us only 3 fingerprints: its weird light curve, its subtle sunward shove, and its faintly reddish hue. From that sparse evidence, theorists have spun half a dozen possibilities, each delightfully exotic, none yet definitive. 1. The hydrogen iceberg. If the body were a block of almost pure H2 snow, sunlight near perihelion would sublimate hydrogen so quickly that the expanding gas could deliver the measured push while staying invisible to optical or infrared telescopes. The catch is manufacturing. Molecular hydrogen condenses only at a few kelvins, temperatures reached in the dense cores of giant molecular clouds. Critics argue that cosmic rays would erode such a berg long before it drifted into our system, shrinking it to nothing over the millions of years of interstellar travel. 2. The nitrogen shard. Another idea casts Oumuamua as a splinter from the nitrogen-frosted crust of a Pluto-like dwarf planet. Nitrogen sublimates efficiently and, unlike water, carries almost no dust. Computer models show that tidal collisions in young, volatile-rich systems could fling thin N2 plates into space. Yet spectral searches saw no telltale nitrogen lines, and calculations imply the Milky Way would need to grind up thousands of Plutos per year to supply the galaxy-wide population this scenario predicts. 3. The fluffy dust bunny. Perhaps the acceleration is not outgassing at all, but pure sunlight. A fractal aggregate of micron-sized grains, think of a snowflake made of soot, could have the area-to-mass ratio of a soap bubble. Radiation pressure would then mimic a tiny rocket plume. Laboratory studies confirm that such aerogel asteroids can form in low-velocity collisions. But would a loosely bound clump survive the violent entry past perihelion? 4. The mundane weak comet. A more conservative camp notes that carbon monoxide or carbon dioxide jets could produce thrust, yet remain below current detection limits. Oumuamua might simply be a very small, very depleted comet that fooled our instruments by hovering at the threshold of sensitivity. 5. The light sail speculation. Finally, Avi Loeb's headline-grabbing proposition. The object is a wafer-thin solar sail, debris from an ancient probe or beacon. The idea is testable only by meeting such an artifact up close, but it reminds researchers to keep an open mind. Nature is not obliged to be less imaginative than our science fiction. For now, the messenger holds its secret, leaving us a menu of hypotheses and a clarion call for faster, closer future investigations. Two years after Oumuamua's flashbulb exit, the cosmos delivered a control sample. On 30 August of 2019, Crimean amateur Gennady Borisov spotted a fuzzy streak in Leo that refused to stack with background stars. Within days, spectra from Keck and Gemini revealed cyanogen and diatomic carbon bands, classic comet signatures. The International Astronomical Union designated it 2I/Borisov, the second interstellar object and the first that looked, smelled, and behaved like a textbook comet. Where Oumuamua had stayed small, dim, and tailless, Borisov bloomed into a 150,000-kilometer coma and sprouted a dust tail longer than Earth's diameter. Its orbit, though hyperbolic, was less steep, eccentricity approximately 3.4, giving astronomers a leisurely 11-month observing window that stretched past perihelion on 8 December 2019. ALMA measured abundant carbon monoxide and hints of water vapor, implying the 400-meter nucleus was born in a frigid Kuiper belt analog around another star. Most telling was its isotropic grain composition. Dust grains matched the size mix in solar system comets, suggesting planet-forming chemistry is broadly universal. Unlike Oumuamua's confounding acceleration, Borisov's trajectory obeyed gravity plus conventional outgassing, reassuring theorists that interstellar bodies need not all be exotic shards or solar sails. In effect, 2I/Borisov set the baseline, proving that at least some visiting debris is simply the stuff we already know: icy, dusty, and refreshingly ordinary. If Oumuamua was a pop quiz and Borisov a practice test, astronomers now want a full-time surveillance camera. Enter the Vera C. Rubin Observatory in Chile. Beginning operations in late 2026, its 8.4-meter mirror and 3.2 gigapixel camera will snap the whole visible sky every 3 nights, catching anything brighter than a 24th magnitude pixel. That cadence means even a dim, fast ISO should appear in multiple frames before it vanishes, giving software time to flag its odd, non-bound orbit. Rubin's secret sauce is HelioLink 3D, an AI-assisted algorithm that threads together faint streaks taken on different nights into a single moving track. In 2023, a prototype version proved its worth by rediscovering a 600-meter Apollo asteroid hidden in plain sight. Europe, meanwhile, is building FlyEye, a compound viewport telescope on Mount Mufara, Sicily. Its insect eye optics deliver a staggering 6,700 degrees squared field, 1/16th of the entire sky, in a single exposure, optimized to trip alarms on any high-speed transient. Above the atmosphere, NASA's planned NEO Surveyor infrared telescope will patrol from a Venus-like orbit after 2028, hunting dark room-temperature bodies that optical surveys might miss. Machine learning classifiers will sift its million-object nightly haul, pushing only the weirdest signatures, hyperbolic speeds, bizarre colors, to human analysts. Layer these systems together and the next interstellar rock won't sneak past in silence. Instead, sirens will blare, coordinates will propagate worldwide in minutes, and if space agencies are ready, a nimble intercept probe might just beat the messenger to deep space. If Rubin or FlyEye rings the next ISO alarm, Europe plans to be waiting with Comet Interceptor. Slated for launch in 2029, the three-craft ambush mission will park at the Sun-Earth L2 point, loiter for up to 3 years, then pounce on the first long-period comet or interstellar body whose path sweeps within reach. Each probe will peel off to image, map, dust and gas, and sample plasma from different angles, turning a single flyby into a stereoscopic science bonanza. The design cleared critical review in late 2024. Its flight computer, fresh from vibration tests, shipped to the prime contractor this spring. Catching Oumuamua itself is tougher but not impossible on paper. The Institute for Interstellar Studies project Lyra has sketched missions that sling past Jupiter, steal a gravity boost from the Sun, then chase the object down sometime in the 2040 or 2050. Chemical rockets, nuclear thermal stages, and even laser-pushed sails are on the menu. All demand launch decisions within the next decade before Oumuamua fades too far and too fast. RAND analysts note the plan is technologically very challenging, yet feasible if agencies treat it like a flagship-class endeavor. Whether we overtake the original messenger or lie in wait for its successor, the engineering race is on. Next time, we intend to meet the visitor rather than watch it speed away. Every chip of foreign stone that drifts through our sky is a free sample from a planet-forming factory we may never otherwise visit. Spectra of 2 I/Borisov, for instance, showed carbon monoxide levels 3 times higher than any solar system comet, implying it condensed in an unusually cold, carbon-rich disk around a red dwarf star. Such chemistry hints that exoplanet nurseries can span a broader range of ices and organics than we once assumed. Meanwhile, models of Oumuamua's elongated, possibly porous body fit naturally with violent planet-building stages that splinter crusts and loft fluffy aggregates into escape trajectories. Planet formation theories thrive on diversity statistics. Do most young systems eject icy snowballs, rocky shards, or airy dust balls? The more interstellar objects, ISOs, we've cataloged, the tighter we can pin down those probabilities. Much the way meteorite collections refined ideas about our own protoplanetary disk. Captured ISOs may even lurk in Earth's co-orbit, waiting for sample return missions to scoop them up. In short, every alien pebble is a data point on the grand question of how common Earth-like chemistry, and perhaps habitability, really is across the Milky Way. Oumuamua's brief cameo lasted weeks, yet its impact will echo for decades. It opened a gate in our scientific imagination. The solar system is not an isolated bubble, but a busy crossroads where debris from countless stars occasionally zips by. In response, survey telescopes are being rebuilt, AI filters rewritten, and whole missions, from ESA's Comet Interceptor to conceptual project Lyra, budgeted around the possibility of the next messenger. More subtly, Oumuamua taught researchers and the public to embrace uncertainty. Sometimes the dataset is thin, the conclusions provisional, and the mystery itself drives progress. Future textbooks will likely list 2017 as the moment planetary science became galactic science, when we first compared native rocks with imports and realized the comparative planetology of entire star systems lay within observational reach. Whether Oumuamua was iceberg, dust bunny, or light sail matters less than the revolution it launched. Humanity now scans the sky not just for neighbors, but for visitors from the far beyond. Thank you for watching. For more content, subscribe to this channel.